Prime numbers such as 2, 3, 5, 7, 11, 13, 17, and so on have accompanied us since elementary school. Their uniqueness lies in the fact that they have only two divisors, 1 and themselves. Though they may seem ordinary, they have captivated countless mathematicians. Why is the study of prime numbers so important? Because they are the atoms of integers. Any composite number can be expressed as a product of primes. For example, 4 is equal to 2 times 2. 6 is equal to 2 times 3. 12 is equal to 2 times 2 times 3. All composite numbers can be represented using prime numbers. Therefore, understanding the nature of prime numbers is akin to understanding the essence of all integers. For this reason, primes are regarded as the crown of mathematics, with several unresolved conjectures serving as the jewels in that crown. More than 2,000 years ago, Euclid proved that prime numbers are infinite using a method called proof by contradiction. 1. Assume that there are only a finite number of primes, which can be listed as P1, P2, Pn. 2. Construct a new number m equals P1 times P2 times Pn plus 1. M cannot be divisible by any pi, as dividing by any pi leaves a remainder of 1. This means m is a new prime larger than Pn, contradicting the assumption that Pn is the largest prime. Therefore, primes are infinite. In the realm of prime numbers, there are several famous conjectures. Apart from the Riemann hypothesis, which I introduced in a previous video, the twin prime conjecture is even more well known. Its appeal lies in its simplicity, so much so that even primary school students can understand its statement. In contrast, the Riemann hypothesis is so complex that understanding its description alone is a challenge. This simplicity has led to far more claims of proof for the twin prime conjecture than for the Riemann hypothesis. Simply put, the twin prime conjecture posits that there are infinitely many prime pairs like 3, 5, 11, 13, 17, 19. Mathematically, if p is a prime number and p plus 2 is also prime, then such prime pairs exist infinitely. However, as numbers grow larger, primes become sparser. Whether there are infinitely many twin primes, primes separated by an interval of 2 remains unproven. In 1919, Viggo Brunn attempted to verify the infinitude of twin primes by investigating the sum of their reciprocals. He defined the sum of the reciprocals of twin primes. The pair p and p plus 2 are twin primes. He hoped to prove that this sum is divergent, thereby showing that there are infinitely many twin primes. However, he discovered that this sum is finite, with a specific value of approximately 1.90216054. This result is known as the Brunn's constant. More than 100 years ago, the great mathematician Euler already proved that the sum of the reciprocals of all primes diverges. However, the sum of the reciprocals of twin primes converges to less than 2, giving the impression that twin primes might be finite. If twin primes were infinite, one could imagine just how sparse they must be. Brunn had hoped to use this method to prove the twin prime conjecture, but instead it shrouded the conjecture in an additional layer of mystery. In 1923, the famous mathematicians Hardy and Littlewood teamed up and, based on probabilistic number theory, proposed a distribution formula for twin prime pairs. Pi2x represents the number of twin prime pairs less than or equal to x. C2 is the twin prime constant, approximately equal to 0.66016181158. They said, since we can't prove it, let's directly write down its properties. Their result, when represented graphically, at least provides data that supports its correctness. Although they could not prove it, these two mathematicians took a different approach and still left their mark in history. The formula suggests that, although twin prime pairs are rare, their quantity increases as x grows and tends toward infinity. In 2005, three mathematicians collaborated to propose an important theorem. The initials of their last names are GPY, so the theorem is known as the GPY Theorem. This breakthrough gave people the impression that the twin prime conjecture was on the verge of being proven. The theorem shows that, under certain conditions, the gap between consecutive primes can be very small, and there are infinitely many such pairs of primes. Although this result does not directly prove the twin prime conjecture, it indirectly suggests that Pn plus 1 minus Pn equals 2 is highly plausible and might even be provable. However, the limitation of the GPY theorem is that its expression does not fix the gap as a constant, but rather as a value that changes with the growth of Pn. This variability represents a key obstacle to proving the twin prime conjecture. If this variable term could be transformed into a specific constant, the twin prime conjecture would be directly proven. This represents a critical path in number theory, transitioning from possibility to certainty. In 2013, Jangs made a significant breakthrough regarding the twin prime conjecture. He proved that there exist infinitely many pairs of primes Pn and Pn plus 1 such that Pn plus 1 minus Pn is less than a constant c. This achievement marked the first time that the largest gap between primes was reduced from infinity to a finite constant of 70 million. To us, 70 million may seem like an astronomical number, but when it comes to probabilities involving infinity, 70 million is essentially zero. Indeed, any finite superlarge number is effectively zero in comparison to infinity. Simply put, for any natural number n, there exists a pair of primes both greater than n, and the gap between them is smaller than 70 million. For example, if you specify 10,000, I can certainly find two primes greater than 10,000 with a difference smaller than 70 million. If you ask for primes greater than 100 million or even 1 trillion, I can still find such a pair. Before Jangs' breakthrough, it was not known whether there existed an upper bound such that there are infinitely many pairs of primes with a gap smaller than that bound. In other words, the possibility existed that no matter how large a number you gave, such as tree 3, after some natural number, there would no longer be any pairs of primes with a gap smaller than tree 3. It sounded completely unbelievable, but before Jangs' proof, no one had even ruled out such a possibility. This highlights the importance of Professor Jangs' achievement. He made a leap from infinity to a finite value of 70 million. The theoretical value of this leap is even greater than the future leap from 70 million to 2. After Jangs' conclusion, the online collaborative mathematics platform Polymath took up the task of narrowing the gap between consecutive primes as its 8th project, and progress was rapid. Within a year, the gap of 70 million was reduced to 246. Now, it is firmly established that there are infinitely many pairs of primes with a gap less than or equal to 246. Even more exciting is that, if the Elliott-Halberstam conjecture holds true, this gap could be reduced to 6. It has already been proven that there are infinitely many sexy primes. The term sexy primes is a joke among mathematicians, derived from the Latin word for six, sex, which is why such prime pairs are humorously named sexy primes. Now, you might be curious about the largest known twin prime pair. The current record is held by a pair discovered in 2016, which spans over 380,000 digits. Interestingly, during the process of computing twin primes, a notorious floating-point calculation bug was discovered in Intel Pentium processors. In 1995, Thomas Nicely, a mathematics professor in the U.S., was calculating the reciprocal of a pair of twin primes, 8246337024441 and 8246337024443 that were over 824 billion. He noticed that the computer output, which theoretically should have been accurate to 19 decimal places, was wrong at the 10th decimal place. This error was very difficult to detect, so initially, Intel was reluctant to recall the processors. Eventually, due to mounting pressure, they announced a recall of the first batch of Pentium processors. This incident also confirmed that mathematicians are the ones who push computer CPU functions to their limits. The above discussed the twin prime conjecture. Now let's look at a proposition that is the opposite of the twin prime conjecture. How large can the gap between primes be? For example, if Pn and Pn plus 1 are two consecutive primes, meaning there are no primes between them, what is the largest possible gap between these two primes? This question was discovered as early as ancient Greece, when it was realized that the gap between two consecutive primes can be arbitrarily large. There is a classic proof using factorials. From n factorial plus 2 to n factorial plus n, the n-1 numbers in between are all composite, and since n can be arbitrarily large, the gap between two consecutive primes can be arbitrarily large. For instance, if we want to find a pair of primes with a gap greater than 100, we would consider the numbers 101 factorial plus 2, 101 factorial plus 3, up to 101 factorial plus 101. The 100 numbers in between are guaranteed to be composite, so the gap between the primes on either side of this sequence must be greater than 100. But clearly this approach is wasteful. The number 101 factorial is enormous, and in practice we don't need to go as far as the magnitude of 10 to the power of 159 to find 100 consecutive composite numbers. So mathematicians, as they often do, began to ask a new question. If I want to find n consecutive composite numbers, where should I look for such a sequence? Or, more generally, what is the maximum gap between two consecutive primes within the range from 1 to n? The prime number theorem tells us that between 1 and n, there are approximately n divided by log n primes. Even if these primes were spaced evenly, the gap between consecutive primes would be at least log n. This means that within the range of e to the power of 100, which is roughly 10 to the power of 43, there must be a sequence of 100 consecutive composite numbers. This is much smaller than the previous upper bound of 10 to the power of 159, which gives a much more manageable estimate for the position where such sequences might occur. The prime number theorem thus provides a potential upper bound for where sequences of 100 consecutive composite numbers might appear, although in reality, the actual gap will be much smaller than this theoretical upper bound. In 1938, the Scottish mathematician Robert A. Rankins came up with a remarkable formula involving natural logarithms. For sufficiently large x, the maximum gap between primes between 1 and x is given by This formula contains so many logarithms that there's a famous joke in number theory circles. What would a drowning number theorist say? I need log. Mathematician Paul Erdos once offered a reward for anyone who could completely solve the problem of the maximum gaps between prime numbers. While most of his bounties ranged from $25 to $100, he placed a $10,000 bounty on this problem, highlighting its significance and the difficulty he believed it posed. The latest progress on this problem came in 2014, when Terence Tao and others made an improvement. They modified the 1/3 in Rankins' formula into a function that grows with x. He also conjectured that it might be possible to remove the square from the denominator in Rankins' formula. Carrying on Erdos's legacy regarding this problem, he announced a $10,000 reward for anyone who could prove this conjecture. The above discussion covers research on the largest prime gaps. having explored the largest and smallest gaps between primes. Is there anything else about prime gaps that mathematicians can investigate? It turns out there is. Mathematicians have also studied whether prime numbers can form very long arithmetic progressions. This question was resolved in 2004 by two mathematicians, Ben Green and Terence Tao, leading to what is now known as the Green-Tao theorem. The theorem states that there exist arbitrarily long arithmetic progressions of prime numbers. For instance, if you give any number, say tree 3, then there will always exist a sequence of tree 3 primes forming an arithmetic progression. However, it's important to note that their proof is existential, not constructive. In practice, finding an arithmetic progression of tree 3 primes is utterly infeasible. The current record for the longest known arithmetic progression of primes is 26, discovered in 2010. This sequence can be expressed as 43142746595714191 plus 236811770 times 23 times n, where n ranges from 0 to 25. Additionally, the Green-Tao theorem is actually a special case of the Erdos arithmetic progression conjecture. This conjecture posits, if the reciprocal sum of the terms in a sequence of natural numbers diverges, then the sequence contains arbitrarily long arithmetic progressions. Since Euler already proved that the sum of the reciprocals of the primes diverges, the Green-Tao theorem is a natural consequence of this. Lastly, I'd like to propose a conjecture of my own, which could be seen as an enhanced version of the Green-Tao theorem combined with the twin prime conjecture. It suggests the existence of arbitrarily long consecutive twin prime sequences. Specifically, this means there exist sequences of n consecutive twin primes p, p1, pn-1, with k being an integer greater than or equal to 2. Furthermore, n can take any value such as 100, 10,000, tree 3, or even SSCG3. Given the infinite and seemingly random nature of primes, this conjecture feels quite reasonable. Moreover, there are many similar conjectures that could arise, likely enough to keep bored mathematicians occupied for quite some time.